All right. Good evening, everyone. Welcome back. Our seventh meeting together on this last day of February, February 28th. Hopefully you were aware of and took your test. Remember, we don't do makeup tests unless you have some kind of medical documentation or some type of documentation, not necessarily medical. Court documentation works as well. But I did go through and look for any kind of partial credit I could do. If you think that you had something that I didn't get to, remember you can email me and let me know, and I'll check it out. Happy to check it out. But yeah, test scores were pretty good overall. I was pretty pleased. Hopefully you were too. And per usual, it was usually the people that did more homework that did better, but it's not a 100% correlation. Just so you know, test 2 will be, I guess, soon-ish. It's not going to feel that soon since we have spring break next week. So please understand we do not have class on Monday the 7th because that is the week of spring break. So we will not be back in class until the 14th. We will finish all of the material for chapter 3 on Monday the 14th. So we will finish all the material for chapter 3 on the 14th. The last section will be 3.8, and we're going to be skipping some sections. We do 3.1, 3.2, 3.4, and 3.8. Remember, all your grades for homework and tests are in my math lab under your grade book. And then, so sorry, I'm a little distracted. I'm scrolling through my calendar trying to make sure I've got everything right. The 14th will be the last day we cover anything from chapter 3, which means you'll be testing on chapter 2 and 3. It'll be your second test the week of the 21st. So probably the 21st, the 22nd, and 23rd. There is a chance this will be one of your 2 proctored exams. Remember, I mentioned that you will have to take 2 of your exams while being video recorded, either with your cell phone or a webcam or something like that. So that I'm thinking I want to go ahead and knock out test 2 as one of those, and then the final exam will be the other one. The final has to be documented. So yeah, expect your second test on chapter 2 and 3 material that was covered, nothing that wasn't covered, obviously, because we skip a lot of sections in chapter 2. We'll skip a lot of sections in chapter 3. But again, that's probably going to be the 21st through the 23rd, but you'll see it officially on the whiteboard the week of the 14th when we finish chapter 3's material. And cool news today, I'm actually going to be letting y'all out about 15, 20 minutes early because we're going to finish 3.4, and I could start the material for 3.8, but unfortunately, I need to spend about 10 minutes talking about the theory of everything. And then the first example is going to take more than the amount of time we would have tonight. We could get through part A, but I don't want to leave you over 2 weeks before we come back and do part B. If it wasn't spring break next week, I would go ahead and do part A, but because of that, you're going to get out a little early tonight, so hopefully that'll make everyone happy. So we won't start 3.8 at all tonight. Once we finish 3.4, that'll be it for the evening. So we'll do our usual. We'll have about an hour and 15 hour and 20 minutes worth of lecture. We'll take our 8-ish minute break, and then we will continue. And I believe our break will coincide with ending 3.2, and then we come back and start and finish 3.4. I might have that wrong, actually. I do have that wrong. I'll be finishing the first video. All right, so as always, if you have any questions, I'll be in the chat. But here we go, picking up where we left off, talking about the second derivative test and how we had a situation where you might not have trusted it. So we're going to go back and do a problem that we had seen using the first derivative test.
Second derivative test is bogus. Let's actually pull a problem we've done before. Which will be this one, this x cubed plus 12x squared minus 60x, etc., etc. So for example 2, oops, wrong color. And whoa. I hate when I scroll over that thing. Let's just go ahead and bump this down. instructions. Find extrema by the second derivative test. And this function will be x cubed minus 12x squared minus 60x plus 36. So we're going to go through and take the first derivative. F prime of x equals 3x squared minus 24x minus 60. I am not going to spend a lot of time doing this since it's already been in another section. You set it equal to 0. I could have just copy pasted it. You factor, you get 0 equals 3 parentheses, and it's originally x squared minus 8x minus 20. Then you'll get 0 equals 3 times factors 10 and 2. Yeah, 2 and 10. Make sure they add to a negative, so the 10 is negative, the 2 is positive. When you set each of those equal to 0, the first will be trash. You get 0 equals x plus 2, and 0 equals x minus 10. So x equals negative 2, and x equals positive 10. Those were our critical numbers. Again, because I'd already done that work, I could just borrow it, but because I'm trying to do something else, ultimately, I wanted to re-show the work. Now we find our second derivative. Let's go back to this version. This is easiest to find the second derivative on. So bring the 2 out front. That's a 6 now. 2 times 3. Decrease the exponent by 1. The derivative of negative 24x is negative 24. The derivative of negative 60 is 0. All straight power rules. Now, if I asked you what's the concavity in the different regions, are there any inflection points, all that jazz, that's when you set this equal to 0 and do that test point stuff in the second derivative. That's not what we're doing here. All we do is plug in the critical numbers. So we'll do f double prime of negative 2, which is 6 times negative 2 minus 24, which is negative 12 minus 24, which is negative 36. All that matters is that it's negative. If it's negative, that means it's concave down in that region. So in that region, it has to look like this. In the region of the negative 2, this is what it looks like. But we said that our derivative is 0, the first derivative specifically, at the negative 2. So therefore, based on this picture, it must be a max. Again, because when we plug the critical number into the second derivative, the thing that talks about concavity, because it came out to a negative value, last time it came out to 0. Last time it came out to 0, which is inconclusive. We need it to be a positive or negative number to be able to tell what's happening. So because it's negative, now I don't need to know what happens around it. It's negative at this region, so it looks like this, and the critical number has to be the highest or lowest point because of the whole theory. Therefore, it's a relative max based on that picture. It's not just a straight blatant memorization of if this value is positive, it means it's concave up, which means it's a local min. Yes, you can straight memorize that if you like, but I usually like the pictures 1,000 words argument. But you do you. What is the max? So we got to plug it in. We got to plug in the negative 2 to the original function. So we do f of negative 2. I'm going back to black because we're back in the regular function. So that's negative 2 cubed minus 12 times negative 2 squared minus 60 times negative 2 plus 36. And we already have that answer from before, or at least we should. That was the one that I had goofed it incorrectly at first. That was 100. So now let's go back to the second derivative. But now we're going to plug in the other critical number, which is 10. See, we're only plugging in the critical numbers into the second derivative. So the second derivative, that's the 6x minus 24. So 6 times 10 minus 24. It's a times and a minus, which is 60 minus 24, which is 36. That's positive, so therefore it's concave up in that region. So in the region of the 10, it has to look like this. It has to be concave up. But we know the 10 is a critical number, which means it has to be this. This has to be the 10, which is the lowest point in that region. Therefore, it's a relative or local min at x equals 10. But again, what is it? Go back to the original function, f of 10. That's the 10 cubed minus 12 times 10 squared minus 60 times 10 plus 36. And that's that 764 number. Let me make sure it was 764. Yes, negative 764. And then you could graph it from there. I didn't ask you to graph it because we already did that. But once you have your extrema, if I asked you to graph it, which is a possibility, oops, wrong thing. You can plot that negative 2 comma 100, the 10 comma negative 764, and then you just bend around your polynomial shapes like you know to. At a max, you're going down around the ends. At a min, you're going up around the ends. And then you just connect in a smooth like polynomial fashion. All right, let's do one more of these. And I might be able to get it all on this one. Let me go to a new page just to be safe. Same instructions, example 3, and this function will be x to the 4th minus 8x to the 3rd plus 18x squared plus 2. So find the first derivative. Which is 4x to the 3rd minus, bring the 3 out and multiply by the 8, which is 24. Decrease the exponent by 1. Bring the 2 out and multiply by the 18. 2 times 18 is 36. Decrease the exponent by 1. And the derivative of 2 is 0. We will then set it equal to 0 to find the critical numbers. So we go 0 equals 4x cubed minus 24x squared plus 36x. And then we factor. There's a GCF to take out. And that GCF, 4, 24, and 36, 4 can go into all of those. You got x cubed, x squared, and x. So you can actually take an x out of these. That's something we haven't seen in this chapter, but it's something you should have seen 5,000 times before today. Dividing all these by 4x, you'll get x squared minus 6x plus 9. Keep factoring. The factor pairs of 9 that add to 6 are 3 and 3. So we go 0 equals 4x times x3, x3, but you gotta give them signs. To make sure they add to a negative 6, they both need to be negative. Ooh, look at this. We got a repeated 0. I bet you that this is going to lead to an inconclusive second derivative test for that one. But I bet we can still make the analysis on this one because this one isn't repeated. And you might say, well, this is the garbage part, this 4x. Hold that thought. So let's make our equations. 0 equals 4x, 0 equals x minus 3, and 0 equals x minus 3. Setting each of those equal to 0, for the first one, we divide both sides by 4. It's not garbage, there's an x there. And you end up with 0 equals x. So there is actually a critical number there. Add 3, and you get x equals 3. So our critical numbers are 0 and 3. That's not a point. Those are two different x values, and I want to label that more specifically. X equals 0 and 3. Those are the two possible maxes or mins. It could be both are maxes, it could be both are mins, it could be one max, one min, or they could both be saddle points, or one of them could be a saddle point and the other is a max or a min. These are all possible scenarios. Now, we said to use the second derivative test. Now, we could also say, well, maybe it didn't say use the second derivative test, maybe that's just what we want to do. And quite honestly, for most problems, specifically with problems that don't have this thing going on, the second derivative test is quicker for a regular polynomial. If you don't use a product rule, if you don't need a quotient rule, because you're only plugging in critical numbers instead of test points, and there's always one less critical number than test points. So if there's two critical numbers, that means you'd need 3 test points under the first derivative test, but only 2 plugins under the second derivative test. All right, so again, let's not use the factored version. Let's use the polynomial version, the 4x cubed part. So taking that derivative, 3 in front of the 4, that's 12. Drop the exponent by 1 to a 2. Minus 2 times 24 is 48. Drop the exponent by 1. Plus, this is a linear term. The derivative of a linear term is just the constant coefficient. It's plus 36. Again, I'm not asking what the concavity is. I'm asking what the extrema are. So we just plug in the critical numbers. So f double prime of 0 is 12 times 0. And you could factor this if you wanted to. It might factor easy. It might not factor at all. I'm just going to go straight up this way. Minus the 48 times 0 plus 36. All the first bits cancel. You're just left with the 36. That's not 0, so there's a conclusion. This is positive, so concave up. If it's concave up at a critical number, this is what concave up looks like. So we look like this in that region, but the critical number has to specifically be this point. So that's 0. So that means it has to be a relative min at x equals 0. And if you want to find out what that relative min is, you plug it into the regular function. So we do f of 0, which is 0 to the 4th minus 8 times 0 to the 3rd plus 18 times 0 squared plus 2. All the beginning part is just 0. The only thing you're left with at the end is the 2. So the point is 0, 2. The relative max, I'm sorry, excuse me. The relative min is 2, and it occurs at x equals 0. Remember, the phrasing is very specific. And I didn't say the phrasing last time, so I will this time. The relative min is 2 and occurs at x equals 0. Now, there can be more than one relative minimum, so I may need to switch my phrasing to a relative min is 2 and occurs at 0. Okay, well, what about the 3? So let's do f of 3. So that is 3 to the 4th power minus 8 times 3 to the 3rd power plus 18 times 3 squared plus 2. And let's just pull out a calculator for that annoying jazz. It's not the end of the world to do by hand, but let's save ourselves some time. So 3 to the 4th minus 8 times 3 to the 3rd plus 18 times 3 squared plus 2. And we get not the number I wanted. Why did I plug it in the regular function? I'm sorry. Why would I be this is a whole, you know, ask yourself, does it make sense? I'm supposed to be checking the concavity, right? For some reason, because I had just plugged it into a function here, I did it again. So that was a mistake on my part, but I caught myself. And it wasn't a fake mistake. I do fake mistakes sometimes, but that was completely wrong. So let's erase that. Remember, this would give you the function value. So the function value is 29, but that doesn't tell us whether it's a max or a min. We're supposed to be going back to the second derivative. And we're plugging in 3. So that's 12 times 3 squared minus 48 times 3 plus 36. All right, sorry about that. But I do like when that happens because I hope that you learn from that and learn to ask those questions yourself. So 12 times 3 squared minus 48 times 3 plus 36. And that's the answer I expected because of the repeating critical number. We get 0. If it's positive, it's concave up. If it's negative, it's concave down. If it's 0, it's inconclusive. It's possible it's a saddle point, but it's possible that something else is going on. So what you have to do is go back to the first derivative test. Now, we already have the information about 0, so we don't have to set up everything. We just need to set up around the 3. So into the first derivative test, we're only worried about x equals 3 as a critical number. So when I draw this up, and I put my 3 up here as my critical number, the 0 is over here also, but I don't care about it. I don't need to check to the left of it. So I'm gonna put a little asterisk above it and just say, there it is, because I also wanna make sure I don't go too far. So when I do my test points, they still have to be to the right of the critical number and to the left of it, but I can't use 0 because it's a critical number. I can't use -1 because it's to the left of a whole nother critical number. It has to be between 0 and 3. So the only good whole numbers are 1 or 2. Let's go with 2. So now we can plug the 2 and the 4 into the first derivative. So f prime of 2 would be 4 times 2, then times 2 minus 3 times 2 minus 3. 4 times 2 is 8, which is positive. 2 minus 3 is -1, so negative, negative, and that's a positive. So it's increasing. In the region of the 2, it's increasing. I'll do this as straight lines this time instead of the curves. Now let's do the 4. So that's 4 times 4, and then times 4 minus 3 times 4 minus 3, which are all positive, which means it's increasing again. So to the right of the 3, it's also going up. So this is a problem. It's increasing, it hits its 0 derivative, and then it starts increasing again. So this is the most likely appearance around the 3, which means it's again a saddle point, not a max or a min. So there's only one extrema. And that was the relative min of 2 at x equals 0. I could give you a problem with 17 critical numbers and there's only one extrema. I can give you a problem with one critical number and there's no extrema. I can give you a problem with 17 critical numbers and there's 17 extrema. Anything is possible. So if I asked you to graph, I didn't ask to graph, but if I asked for it. So we have the relative extrema at 0, 2. There's a height of 2. And that's supposed to be a relative min. So in that area, it's supposed to look like that. Then we have that other point, and you did see the math earlier. What was that output? Was it 29? Let me put my calculator back up. Just recalling some functions with second enter. This was me plugging in the 3 to the real function, and it was 29. So just note f of 3 is equal to 29. So over here, 1, 2, 3, there's a point way up here at 29. This is going to be a little skewed. So here's my 329. So we know we're bending up around the relative extrema. We know we're going to be increasing until we hit that point. But when we hit a critical number, they tend to flatten out. But then it keeps increasing, so it would go up again like that. I'm going to redraw this graph lower. That's not enough space. Let's just say here's our height of 2, and here's our height of 29. So here's the 0, 2. Here's the 1, 2, 3, 29. Those were our critical numbers, so we know the derivatives are 0. We know this was a relative min, so it had to go up around both. We're going to go up, 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 up. Let's start flattening out as we get a little closer to the critical number. You can just barely see it, but I'm flattening out. But then we said we were increasing again on the right of it, so we keep going up. And again, this little bump is not perfect. The left side, there's nothing to tell us to turn around. There's no relative extrema. Those are our typical turning points. So we just keep going up and up and up and up and up like this. And again, this little region right here just looks a little goofy. It's not super smooth. It should look more like this. That's more what it should look like in that region. Just to be a little better. The circle, I'm not drawing a yin-yang, yin and yang. I'm just saying this is me blowing up that region and making it look a little better. So maybe you don't trust this. Graphing calculator, go to your y equals screen. That is the other one. We are dealing with x to the fourth, x to the fourth, minus 8x to the third, plus 18x squared, plus 2. Okay, so here's our 0, 2 min, and that's all we can see because this has a height of 10 and negative 10. So let's change the window. We need to at least have a height of 29. Let's make it like 40. So I got a window, y maximum, and make that a 40. I'm only going between 0 and 3 really on the x-axis. And look at that. Look at that. That's pretty good. Like I said, it should be flattening a little more. It's just, I'm already a not great artist. You throw me a pen that I can't even watch myself draw, and things like that happen when I'm trying to have it zoomed out. But there we go. We can see that we have our min here. We can see that this is a critical number because the derivative is certainly 0 here. A tangent line would certainly be 0. Have it be horizontal and have a 0 slope there. But it doesn't turn back around. It keeps trucking in the same direction, which is why it's not a max or a min. It's not an extrema. So that's one of my favorite problems from this section because it has both the issue of the second derivative test being inconclusive as well as a critical number that you could actually determine with the second derivative test. Again, I like the second derivative test when it can be used easily. If it's a power rule, I typically go to the second derivative. If it's a product or a quotient rule, I'm going to stick with the first derivative because taking those derivatives is more time consuming, especially the quotient rule. If it's an exponential, I think it's pretty fine either way, whether you use a first or second derivative test if it's your choice. And some problems I would give you the choice, some I won't. When it comes test time. Okay, so as a reminder, I was worried that graph was going to get messed up. As a reminder, an inflection point is where a function changes concavity. It changes from concave up to down or from down to up. It can't be concave up, then 0, then concave up, or down, and then 0, and then down. So it's where a function changes concavity. It goes from positive to 0 to negative, or negative to 0 to positive, one or the other. In economics, this is the point of what we call diminishing returns. Diminishing returns is the act of still gaining more of something as you move on, as you or time or whatever, or as you, let me phrase this a little nicer. As, I don't want to just say as the input variable goes on or as it increases, because that's kind of weak. Let's say as time goes on or production goes up, things like that. So diminishing returns is the act of still gaining more of something, more money, more satisfaction, more something. But the rate at which you're gaining more is decreasing. So maybe day 1, you gain 15 items. Let's say $15. Day 2, you gain $12. Day 3, you gain $10. Day 4, you gain $7. Day 5, you gain $4. Day 6, you gain $3.50. From the Loch Ness Monster. Sorry, terrible joke. Old joke. Maybe one of you gets it. This is diminishing returns. So when I say gain, I mean profit, income, whatever. You're gaining more the next day, you're gaining more as time goes on, but your gains are decreasing. So this is the idea of diminishing returns. We still gain each day, but our gains are slowly decreasing. Oh, that's going to screw it up. Let's just use, and you get the idea. There we go. Word is fun sometimes. I also liken this to the Dorito problem. You open the half a pound bag of Doritos or 10-ounce bag of Doritos, however big it is now. It used to be a pound, and then they made it 14 ounce, and then they make it 12 ounces, and they never change the price. They just give you less and less chips. This is also true of ice cream. Ice cream containers used to be bigger, and to keep them the same price, they just make them smaller. And they expect most Americans not to realize it, and most of them don't. So you're paying the same price, but you're getting less. You're like, man, that ice cream container went quicker. That bag of Doritos went quicker. What's going on? Is it me? Am I eating more? No, it's just a company hiding them, upcharging you because of inflation and such and greed. A little of both. So the Dorito problem, you open your 10 ounces of Doritos and that you're hungry and that's the air just fills with that salty scent, and you eat that first one and it's glorious. It's the best chip you've ever had, right? And then you eat the second one and it's still amazing, and the third one's amazing, and the fourth one's amazing. And then you eat your 12 or 13 chips, whatever a serving is supposed to be. But we're Americans, so we don't eat just one serving. We have some more. We have our 13th chip. But I tell you what, you're still happy with that 13th chip. You're happy because you're still eating it. You're gaining some satisfaction. It's filling your belly. Your taste buds are still firing off. But it's not as good as that first chip, is it? That first chip was like a miracle. The 13th one, it's great. It's great. That's not bad. Great's good, but it's not a miracle. And then you eat your second serving, and then you're on your 25th chip. And now you're like, I mean, I can keep going. They're still tasty. I don't necessarily need to keep eating, so I'm going to keep doing it. That 25th chip isn't as good. And then you eat your third serving, and your 36th chip, I mean, it's fine. It's okay. Why am I doing this to myself? But you keep doing it. You must be getting something positive out of it, but the amount of that positive is slowly and slowly shrinking. Now, diminishing returns can lead to negative output ultimately, or it could just be slowly going to zero gains. So maybe day 1 million, we're gaining 15 cents, something like that. And that's when we have asymptotic behavior, like in 3.4, which is it 3.3? 3.3, excuse me, that we'll hopefully get to circle back around to. All right, so I have an example. What example number are we up to? 4? Yes. Got a nice word problem. A company predicts if it invests X $100,000 in advertising, its revenue will be color 30x squared minus 2x cubed plus 100 in hundreds of thousands of dollars. That's a terrible looking zero. I don't know what was going on with my pen there. I've kind of figured out how to use the erase button, but I'm still working on it. Anyways, in hundreds of thousands of dollars. This is only going to be for X between 0 and 9. That's called a constraint. Constraints are very important for realistic models because the models that we make tend to be oversimplified and only good on a short scale. So if you go past 9, maybe this model is no longer accurate. Population dynamics, if we want to describe the population as linear growth, that's only good for like 10 years, maybe 30 years. If you want to talk about population growth as an exponential curve, it's good for maybe 50 to 100 years. But if you want to talk about a population dynamic over thousands of years, you have to go to that logistical curve that I've mentioned in passing, where you see the explosion for a while, but eventually we slow down due to constraints, due to reasons that will start capping our population, whether it be the size of our planet, the amount of resources we have, whatever. Find the point, back to the question at hand, find the point of diminishing. In other words, when the company will still make more money if it makes more items, but the more money part is going to get smaller and smaller. So, all right, if you make 8 items, you'll make $100 more in profit, whereas if you make 9 items, you might only make $80 more in profit. Well, you still want that $80 more, but you just need to understand that you're not going to be collecting money as efficiently. It's not necessarily bad, but maybe it is. It depends on your company. All right, so what were we saying about diminishing returns? What does it have to do with? It's an inflection point. So in economics, the point of diminishing returns is the inflection point, which means ultimately we need to find the first and second derivatives. So we'll do f prime of x, which is, and note that this is a funny ordered polynomial. I chose this one intentionally because the middle term is actually the guiding term because that's the one with the largest exponent. Do you have to reorder this? No, it might be helpful. Let's just pause on that and see if we can leave it alone for now. Bring the 2 out front, that would be a 60, decrease the exponent by 1, so 60x, minus, bring the 3 out front and multiply, so that's a 6, 3 times 2, decrease the exponent by 1, the derivative of 100 is 0. So there's our first derivative. I didn't say find local extrema, I didn't say find maxes or mins, so I'm not going to set this equal to 0. I'm going straight to the second derivative. The derivative of 60x is 60, minus, drop the 2 out front, so that's a 12, decrease the exponent by 1. So our second derivative is 60 minus 12x. Now we're supposed to be finding the inflection points. Inflection points are where the second derivative is 0 and it changes around it. So we set this equal to 0. So we go 0 equals 60 minus 12x. You can add 60 to, subtract 60 to both sides or add 12x to both sides. I'm going to add the 12x just to go ahead and get the positives. If you subtract 60, that just means your next step is to divide by negative 12 instead of us dividing by the positive 12. Ooh. There we go. Give me the black, please. Thank you. Divide by 12. And 60 divided by 12 is 5. So we get x equals 5. This is our potential inflection point. Potential inflection point. To know whether it is the inflection point or not, you have to, on the second derivative, test around it, find the concavity around it and make sure it changes concavity. So we got to do test points. 4 and 6 would be great test points. Or 0 and 6 if you want to do 0, because 0 is always an easy number to plug in. We plug these into the second derivative because we're checking concavity. So f double prime of 4. That's 60 minus 12 times 4, which is 60 minus 48, which is 12. That's positive. By the way, if you want to write that extra detail, you can write that's greater than 0. So it's concave up, which means in the region of the 4, it looks like, I'm going to draw it above, it looks like this until you hit the 5. So there's your 5. It's concave up in that region. Now again, we didn't plug a critical number in. Our point's not here, the 5 is over here, the 5 is not a critical number. I have some random number to the side where it's still concave up. Now let's do the 6. F double prime of 6, which is 60 minus 12 times 6, which is 60 minus 72, which is negative 12. And that's negative. If it's negative, it's concave down. Which means in the region of the 6, it's concave down. And again, that's not a critical number, so the 5 is supposed to be over there. So we go from concave up to concave down. It's switched, so it is an inflection point. So since concavity switched around x equals 5, x equals 5 is an inflection point, thus the point of diminishing returns. Now, this function was a revenue function based on how much they spend on advertising. It's kind of a weird, atypical function. Usually revenue functions are based off of quantity of items produced, but this is talking about advertising, and in advertising you spend money to make money. So advertising, the input and the output is both money. If you spend $100,000, maybe you'll take in $1 million. Whereas non-advertising revenue functions are based on, well, if you sell this many items, you'll take in this much money. So advertising doesn't have anything to do with the number of items. It has to do with how much you spend and how well you advertise. Now, this function, X, was represented in hundreds of thousands of dollars. So that 5 is really $500,000. So when the company spends more than $500,000, and still expect to bring in more revenue, but that revenue increase is slowly decreasing. So let's pull out our calculator to make this simple. And I want to show you a trick you can use with the TI-83. And you don't have to do it this way, but I'm just going to type the function 30. I'm actually going to use x. Here's my x button, 30x squared minus 2x to the third plus 100. I can actually store values of the x in this calculator. See, it just spit out a number. How did it get that? If I just type x, my calculator right now thinks x is 10. So if we spent $1,000,000, in other words, $1 million, we could expect to have this as our output again in hundreds of thousands of dollars. So that's a large amount of revenue. If our x is 5, so let me show you this, 5, then the store button, and then x. And if you don't want to do this, you can just go back and type in the numbers and do the math. So now I'm telling my x is 5. So if I hit x, that's 5. So I can now recall that original function. Just takes a few times because I had typed other things. Now this will no longer say 10, 10 because it's not thinking the x is 10, it's 5. And the answer is 510. So when we spent $500,000, we got $100,000 out of it. But when we spent $100,000, we got whatever that other number was, which was bigger. But that means, again, we're still making more money, it's just it's slowing down. So now if you maybe make the x 100, or let's go to, let's actually just do two numbers. And let's go to 6 and 7. 6 store x, and recall the function. So we were at 510 originally, now we're at 658. Let me write these numbers down just for a second. So at x equals 5, f of 5 is 510. Then at x equals 6, f of 6 was, what was that funny number again? I might have to put y'all on pause for a few minutes, just a warning after I finish this example. I got a family thing. Sorry, but it'll just be a few minutes. 658. Now let's do x equals 7. So 7 store x, recall. Now we're at 794. Let's do the differences of these. So f of 6 minus f of 5, that's the 658 minus the 510, that's 148. Let's do f of 7 minus f of 6. This is the change going from each increment. Again, that's the change, so 794 minus 658. Why is my pen being like that? 790, there we go, 4 minus 658. I think sometimes I'm trying to use my mouse and pen at the same time. And that difference is what, 136. It's a smaller difference, which means the change is decreasing. Again, we're still making more money. You should still arguably keep spending money on advertising because it's going to get you more. But there is a point at which, and you would have to figure this out at a company, at which you decide these diminishing returns are no longer worth you spending more and more and more money. Because if it hits the point where you've got to spend an extra $10 million just to make another $50 in profit, that doesn't seem reasonable. Why would you spend $10 million just to increase your margin by 50 bucks? Because at some point in this function, that would happen. So that's when you say, all right, well, I don't want to do this anymore. And also, as you keep going, eventually, eventually you might not be producing efficiently, and all of a sudden you start losing money by spending too much on ads. Maybe you're oversaturating the market and everybody gets sick of seeing your ads, so they don't want to buy your product. I can't tell you how many products I've not bought because I see their ads too much. Although I'm not very easily influenced in terms of advertisements, so I'm a bit of a an outlier in that case, probably. But I really like this problem because it shows that idea of diminishing returns. And again, you're still making another $148,000. You're still making another $136,000 in terms of revenue. You know, there's nothing saying, hey, stop at 5, maybe go to 6, maybe go to 7, maybe go to 8. But you can see that eventually this number is going to keep dropping, and ultimately it might not be worth it to, once again, spend another $10 million just to make $50 in profit. Especially in the real world where these models are not, guaranteed. Maybe you spend that $10 million and something weird happens in the real world and you don't get that extra $50. It ends up costing you $200,000 or something. I don't know. Anything's possible. Let's see. I had another example with something different that was not diminishing returns. I'm going to trim that problem out for time, as we will never finish this course if I do it. That should be it for 3.2. And the family thing I said I might have to pause for, that's they paused for me. So hopefully that doesn't come back up. 3.3, 3.4, excuse me. I say 3, then 4 in type 5. Like I said, we're going to temporarily, if not permanently, skip 3.3. We will come back to it if time is there for it. Optimization, finding absolute maximum and minimum. Values. So up until this point, we've always attached one of two words, relative or local, to these extrema, to these maxes and mins. So remember, relative or local extrema are only max or min in a very small region. There can be multiples of each. When we talk about absolute extrema, the difference here is that we're not looking in just a local region, we're looking at the entire picture. So your absolute max or your absolute min, these are the highest or lowest values of the entire function or restricted window if given. There can only be one of each. There can only be one absolute max and one absolute min. Optimization is all about finding the absolute max and or absolute min. Optimization, there are literally dozens of graduate level mathematics classes on this subject. There are books, not just textbooks, just book after book after book by various authors on optimization. This is one of the most insane fields of mathematics in existence. And it's one of my favorites, besides chaos theory. And I don't even like chaos theory for the pretty pictures that everyone sees. That's awesome and fascinating. I like chaos theory for another reason, but we won't get into that in here because that's not what this course is about. But optimization. I kind of already hinted at this. If you're a business, don't you want to make the most money possible? Don't you want to be producing enough units to make that happen? Because you can make too many. You can make too few. If you make 5 items, maybe your profit's $10. If you make 10 items, maybe your profit's $100. If you make 1,000 items, maybe your profit's $75 because you need a bigger building, or you got too many employees in that building, or you need to redesign the machine that outputs your items because you need to up production by 5,000%, something like that. So you get into these mathematical models that don't just look for a single or the multiple relative extrema, the relative mins or relative maxes, whichever you're interested in. You find all of them and then find which one is the highest or lowest. Okay, so the rant aside, optimization. Finding absolute max or min. Often your domain, again, reminder, x values, will be restricted on some bounded interval a to b. We just had a problem with that type of restriction. We didn't actually use anything about it. Let me pull up the section again. I'll bring this back so you can keep writing in a second. No, not 3.1, 3.2. This problem, we said, there it is, that this revenue model was only valid for x values of 0 to 9. So for spending between $0 and $900,000. So this model isn't even going to be good if you use $1 million, anything like that. So some of the numbers I was talking about plugging in, I actually couldn't. But that wasn't necessarily the point. And the good thing is our answer was in that region. But if I got an answer that was outside that region, it wouldn't have been possible and back over there. But this is what I'm referring to in terms of a bounded region. Your x has to be between 0 and 9 or 1 and 5 or whatever numbers it might be. This was written in an inequality form. This is a little more formal and written in interval notation. So this is the same thing as saying a is less than or equal to x is less than or equal to b. They don't have to be bounded. They can be open-ended, they can be parentheses, but I don't like doing that in a business calculus class. It's kind of pointless. For obvious reasons, I think. Why would you want to have the output, the maximum be at a number you can't even use? It wouldn't make sense. So the one thing that differs between local and absolute extrema that you must plug in all possible how do I want to say this? All possible x values, all potential extrema x values, there we go, into the function to get the outputs, as well as the bounds a and b. From above. So like the 0 and 9 from that very last problem we had, if that was what we were doing. So not only do you have to find the critical numbers, you also have to plug in the boundaries. Do the function and see which gives the largest and smallest output. So the basic process is, first step, find f prime of x. Find the first derivative. Second step, find your critical numbers, which is setting the derivative equal to 0 or undefined if it's a rational function. Then evaluate f of x at the critical numbers and the boundary values. The absolute max is the biggest, largest. The absolute min is, guess what, the smallest. Asterisks. You can also use the first and or second derivative test for critical numbers, but you can't do it for the boundaries. So it's kind of not worth it. And I won't do that for any problem that I say find the absolute extrema. Because all it's going to tell you is potential maxes and potential mins. It still doesn't tell you if it is the max or the min unless it's the largest or smallest value. You're still going to have to plug them in, so it's kind of an extraneous step, meaning that it gives you information that would make you maybe feel a little more secure, but it doesn't actually do anything constructive. And there was supposed to be a 3 for the evaluate. So that's your 3-step process. Now, believe it or not, that is pretty much all of the instructions for this section. There's not too much else going on. Yeah, we're good. Okay. I was looking for another piece of paper and I found it. So first derivative test is for local extrema. Second derivative test is for local extrema. When you're talking about absolute extrema, you still need to do a first derivative. You still need to find critical numbers, but you don't have to do test points. You don't have to go to a second derivative and talk about concavity. All you have to do is plug the critical numbers and boundaries into the irregular function, see which one spits out the largest value, see which one spits out the smallest value. That's it. So we can go straight into an example. We may get 2 of these done, we may only get 1 of these done, but we're going to find the absolute extrema for of x equals x cubed minus 9x squared plus 15x. And we're going to do this on the boundaries of 0 to 3. And I want to talk about this problem if I didn't have the boundaries, because all optimization problems don't have to have boundaries. I don't have to do this. I don't have to say find the extrema on a boundary. I can just say find the absolute extrema on this. And what happens is maybe there's only one of the extrema. Maybe there's only an absolute max. Maybe there's only an absolute min. Maybe there's neither. There are functions that have neither, and I'll demonstrate that after a while. So we're going to find the absolute extrema, and this is bounded. Again, I don't have to give you bounds, but I generally do. I can't think of a test question I'd give you that wasn't bounded. Not for this class. If you're a traditional calculus class, I would. So first, find the first derivative. It's a straight up power rule. I like the power rules for these problems because it makes it easier. 3x squared, just get down to the point, minus, drop the 2 out front, 2 times 9 is 18, decrease the exponent by 1, plus derivative of 15x is 15. We're going to set this equal to 0 to find the critical numbers. So we go 0 equals 3x squared minus 18x plus 15. Then we're going to factor. 0 equals, there's a GCF of 3 to pop out. x squared minus 6x plus 5. Can't take an x because the 15 doesn't have one. Pairs of numbers that multiply to 5 but add to 6 are 1 and 5. So we go 0 equals 3 parentheses. I really like 3 as a GCF, don't I? So you go x1, x5. To make sure they combine to a negative 6, they both need to be negative. Then we go 0 equals 3, which is trash. X minus 1 equals 0, which means x equals 1. X minus 5 equals 0, which means x equals 5. So our critical numbers are x equals 1 and 5. Now, I need you to notice something, because you can go very, very wrong at this point if you don't notice it. Pay attention to the bounds. We are stuck between 0 and 3. We are only dealing with numbers from 0 to 3, including the ends. 0, 0.9, 1.137, 2.999999999, 3. But we can't use 4. We can't use 7.9. We can't use 12. We can't use negative 80. Sometimes these critical numbers are outside the bounds, in which case you just throw them out. X equals 5 is not in 0 to 3. So we toss it. Sometimes all the critical numbers are in the bounds. Sometimes none of them are in the bounds. Sometimes one of them or two of them are in the bounds. Guess what? It varies from case to case. All we do now is plug this in to the original function. So we got to plug in the 0, the 1, and the 3 into f of x. The 0 and the 3 were the bounds. The 1 was the critical number that was inside the bounds. So f of 0 is 0 cubed minus 9 times 0 squared plus 15 times 0, which is 0. F of 1 is 1 cubed minus 9 times 1 squared plus 15 times 1, which is 1 minus 9 plus 15, which is 7. And then f of 3 is going to be 3 cubed minus 9 times 3 squared plus 15 times 3. Watch your PEMDAS. 3 cubed is 27. 3 squared is 9. 9 times 9 is 81. So that's minus 81. Plus 15 times 3 is 45. So f of 3, what's that? 27. It's negative 9, right? Let me double check that. Let's add the 27 and 45. So that's 52, 62, 72. Yes, negative 9. That is it. That is the entire workload for this problem. In my opinion, absolute extrema are easier to do in our class, not the crazy graduate level optimization problems that I kind of alluded to. We don't do anything like that. In our class, optimization problems, when you're given the function and the bounds, is easier than a first and second derivative test. Because you don't have to do test points, you don't have to worry about changing from increasing to decreasing, or changing from concave up to concave down, or just what's the concavity at the test point. All you're looking for is the biggest and the smallest values. So all we're looking at is the 0, the 7, and the negative 9, and finding out which one's biggest and which one's smallest. That's it. Well, 0 is in the middle, 7's the biggest, negative 9 is the largest. So f of 1 being 7 produces the max. f of 3 being -9 produces the min. So what we can say, I'm going to type it out. The absolute max, 7. Remember, the max or the min is the output, not the input. You've got to get that right. If you get it wrong, that is going to penalize you severely because it's wrong. The absolute max is the output of 7, and it occurs at x equals 1. The absolute min is the -9. It occurs at x equals, what was that, 3? Yes, 3. So in the window of x equals 0 to 3, the largest output occurs at x equals 1, which happened to be a relative extrema too. It would be a relative max if you checked it. But the absolute min is not at a relative extrema, it's at one of the boundaries. There's no way to use the first or second derivative test to check that. It is literally impossible. You just have to plug it in and see which is biggest and which is smallest. Let's pull out our calculator. Let's graph this thing just to see if this agrees. What are we looking at? X cubed minus 9x squared plus 15x, which, by the way, when you're in the graphing section, your x's are not stored as those hard values in the regular screen. Let's zoom standard. So here's our function, and you can see it's got a relative max here, because that's a top of a hill, and there's probably a relative min somewhere about right here if I pulled back on the calculator. Let me just do that. Let's make the, let's say, trace, probably around 5, -25. So let's make my window the y minimum -30. That might do it. So we can see a peak, we can see a valley. So here's our relative extrema. We got a relative max here, and that relative max occurs at 1. You could prove that with the first derivative test. We didn't actually prove it was a relative max, but we can see it is. And then the relative min occurs right here. What's that look like? About 6, 5? It looks like 5. So the relative min occurs at 5, and it's got a height of -25. Now, -25 is a smaller value than what occurred at 3. At 3, the output was -9. At 5, the output's -25. So if we actually were able to have this in the window, that means that this could be the this could be the absolute minimum. But 5, we weren't supposed to be looking at this. We're not even supposed to be looking at this section. We're only supposed to be between 0 and 3. So what I can do is go to the window with the x values, make the x minimum 0, make the x maximum 3, and that way I can only look at the area I'm supposed to look at. And see that relative min is nowhere to be found, so it's definitely not the absolute min. The highest point in this window is right here, and like we said, if you trace it out, it has a height of 7. And the lowest point is over here, right there, when it's x equals 3, and that height is -9. Again, with absolute extrema in this course, we tend to be looking at just a small section of the function, not the whole thing. Now, let's go back to this graph, and let's just do a standard zoom. And it's going down on the left, it's going up on the right. You know, maybe make that the y values a little bigger like we had last time. Let's take the y maximum to 50 and the y minimum to -50. Just deal with the same x range. This function is going down forever on the left. This function is going up forever on the right. This function, if I didn't bound it between some two values, 0 to 3 or 2 to 1,000,000 or -5 to +5, if I left this function unbounded, there would be no absolute extrema. I want to actually write that part down. So note, this function was unbounded, meaning we didn't have that 0 to 3 part, there would be no absolute extrema. Because the graph looks like this. Because it goes down forever, there's no min. Because it goes up forever, there's no max. Now, not all polynomials look like that, though. Some polynomials only go down on both ends, so you can have an absolute max on an unbounded polynomial. Some polynomials only go up, and you can have an absolute min on a polynomial as simple as that. But these are just quadratics. We don't deal with just quadratics very often in calculus. We're usually dealing with cubics or worse. So it is possible for a function to not have absolute extrema if it's unbounded. It's possible to only have one of them if it's unbounded. If it's bounded, you're generally going to have both unless it's a horizontal line. That's the only case in which you have no extrema because every output's the same. And I would never do that because it's literally the world's most boring function. I want to make sure that I point out that these are entire functions, not just windows. Let's do one more example. We got just enough time, maybe even a few minutes to spare, but we'll call it after this example. Find the absolute extrema function f of x equals x to the fourth plus 4x cubed plus 15 I don't have to give you the bounds written in interval notation. I can give it to you in an inequality form. You have to be able to read both. So same process, because we want the absolute extrema, we don't actually have to do the first or second derivative test. That would only be helpful for identifying relative extrema, and it would do nothing with the bounds. And the relative extrema, if you've got three relative maxes, you've got to figure out which one is actually the max, so you got to do the outputs anyways. So don't try and do more. Less is more. First, find the derivative, f prime of x. X to the fourth, bring the 4 down, drop the exponent by 1, plus 4x cubed, bring a 3 out in front and multiply by that 4 to get a 12, decrease the exponent by 1. The derivative of 15 is nothing. Then we find the critical numbers by setting the derivative equal to 0, which can be factored. There's a GCF of 4x squared to take out. When you do that, you'll be left with x minus 3. X plus 3. I don't know why I said minus. I think I was solving the equation in my head. Setting each of those equal to 0, you get 4x squared equals 0 and x plus 3 equals 0. If you remember your pre-calc, you'll know since there's no plus or minuses, this exponent actually has 0 effect on it. But you can divide both sides by 4 to get that x squared equals 0. The only number squared that makes 0 is 0, but you are technically supposed to take the plus or minus square root if you're going to be thorough. And when you do that, you get x equals 0 either way. Subtracting 3 on both sides, not going to show that work. You get x equals negative 3. These are our critical numbers, 0 and negative 3. Now, last problem, one of these was not in the interval, but it varies from problem to problem, of course. So we got to think, are 0 and negative 3 in the interval, or do we need to toss one or toss all of them? 0 is definitely between negative 4 and 1, and negative 3 is definitely between negative 4 and 1. So both are in the bounds. So when we go to plug these into the function, we got to do f of 0, f of negative 3, f of negative 4, and f of 1. The order you plug them in does not matter at all. Let's do the critical numbers first. So f of 0, that's an easy one. Again, function, not derivative. 0 to the fourth plus 4 times 0 to the third plus 15. That'll be 15. Let's do the f of, I said I'll do the critical numbers first, so I'll do the f of -3 next. So that's -3 to the 4th power plus 4 times 4, not floor, 4 times -3 cubed plus 15, which is positive 81. That's the -3 to the 4th. 3 cubed is 27. That's going to be a negative, though. And 27 times 4, that's 27, 54, 108. And then plus our 15. And then 81 minus 108 plus 15 is -12, right? 107, 27, -27. Yes, good. Then let's do the bounds. F of -4. That's -4 to the 4th power plus 4 times -4 to the 3rd power plus 15. 4 cubed is 64, so times 4 is 256. So that's positive 256 because the negative is evening out. This negative cubed is -64 times 4 is -256. So those are going to cancel. That's nice. Then the plus 15 at the end makes 15. Now what's interesting is f of 0 and f of -4 have the same output, and they are both the largest for now. I'm going to write some asterisks, then I'm going to erase in a second. I'm just saying this number and this number match, and they're both the largest so far. So these are potential maxes. It's possible that the max occurs at 2 different x values. The absolute max would still be 15. We would just say it occurs at 0 and -4. But we're not done yet. I'm just saying it's possible that happens. We still have one more to do. And that's f of 1, which should be the easiest to do. 1 to the 4th plus 4 times 1 cubed plus 15, which is 1 plus 4 plus 15, which is 20. 20 is the largest, -12 is the smallest. So those are the extrema. So thus we can say the absolute maximum is 20 and occurs at x equals 1. The absolute minimum occurs, sorry, the absolute minimum is -12 and occurs at x equals -3. And there's our answer.
I forgot to unmute my mic for a second there. At least I didn't make it too far before realizing. All right, so that is where we're going to pause before our break. Like I said, we will come back. We're going to do about 8 minutes, so we're going to come back right at 8 on the dot. And we'll pick up where we left off. All right. Well, we're going to pick back up where we left off in 3.4. Going to just have a super quick reminder discussion about what optimization is, and then get into another example. And like I said, we will just finish 3.4, and that'll be it for the day. We will not start our last section for chapter 3 until we get back from spring break.
So, quick recap. We said that when we talk about finding absolute extrema, we're not just taking our nose to the board or the piece of paper or whatever we're looking at and only looking at the area just around it. We're no longer doing that. We're looking at the whole picture, or at least the picture that they tell us to quite often, and for us pretty much always. We're looking on bounded intervals. Now, in the real world, sometimes you have to come up with the bounded interval for the problem. Like if you're talking about producing some number of units, it wouldn't make sense to produce less than 0, so we could say 0 is the smallest. And then maybe your factory is only capable of making 1,000 units, or maybe the predictive model for your revenue falls apart after 1,000 units, something like that, so that would be your maximum range. So absolute extrema is just the highest high or the lowest low. That's all it is. It's not, you can't have multiple minimas and you can't have multiple maximas. It's just one of each. And there's in general one of each. If you're not looking at a bounded region, then there could be one missing. There could be just a max and no min, or vice versa. Or there could be neither. But that's not the type of problem I throw at you in this course. So what do we do? Well, you still need to find the first derivative of your function so you can then find your critical numbers, but you're no longer going to do the first or second derivative test. You're just going to take your critical numbers, plug them into the function, see what their outputs are. But you also plug the boundaries in, and you see which one's the highest and which one's the lowest, and boom, you're done. I've mentioned that you certainly can use the first and second derivative test for your critical numbers for just more evidence, but it's really unnecessary, and it also can't be used for the boundaries. Remember, you can only talk about local extrema using first and second derivative tests. For absolute extremas, it's an unnecessary test. And we did a couple examples. Go back to last lecture's notes if you need more information. And let's pick up where we left off. This should be, going to do another profit problem. Our example 3. It's going to be a word problem. Yes, example 3. It costs the American Automobile Company $8,000 to produce each automobile. It has fixed costs like rent, etc., are $20,000 per week. Company's price is P of X. Make sure I got enough space here to work later. Equals 22,000 minus 70x. P, price at which exactly X cars. They are sold. There we go. Question A. How many cars should be produced each week to maximize profit? B. What price should they be sold? C. Why did it do that and then that? Oh, technology, doesn't matter. What is the company's maximum profit? tell you, I love problems like this. I really do. I love them, love them, love them because of how relative they are to a lot of people. A lot of people are in business and a lot of people want to make money, and you make money by maximizing profit. Not only are you interested in how many units you should make and what price they should be sold, but you also want to know how much money are you making. Okay, so we're gonna, oops, didn't mean to do that. That was more weirdness. First of all, it is well known, I hope it's well known, that revenue is price times quantity. Money in is the price you sell it for times the number of things you sell. If I have apples that I'm selling at $2 each, if I sell 5 apples, I make $10 in revenue, 5 times 2. In other words, R is equal to P times X. P times X, that's P times X. If you need to be super emphatic, you can put a little multiplication there. That is a multiplication. Well, we have the price function. They gave us P, 22,000 minus 70X. We don't know the X, it's a function. So the revenue should just be this thing times that thing. So your R of X, this is your revenue. It's price times quantity, where this is price. So it's 22,000 minus 70X times X. Can I write it this way? Whoa. Brought my volume down some again. It was fine earlier. Can't do it this way. That's not a proper product because you got a binomial. So you got to make sure you wrap that in parentheses. And of course, you can distribute the X and you get 22,000 X minus 70X squared. Revenue functions tend to be quadratic or higher if they're polynomials, and often they're rationals or radicals like square roots or fractions. So this is kind of a simple revenue function. The true real life ones, if you want to go over extended periods, tend to be exponential or rational or radical, but we're keeping simple models, so we go polynomial. So there's our revenue. All right, well, the question was how many cars should be produced each week to maximize profit? Our ultimate goal is to talk about profit. Profit is the difference of revenue and cost. I don't see anything about cost though. So there's our revenue. Let's get to cost now. What? Cost. This should be cost per car times the number of cars plus any fixed costs. This is the traditional fixed variable amount plus fixed amount model. This is the standard linear cost model. You have your fixed costs and you have your variable costs. Variable costs tend to be the price per item to make on your end times the number of them that you're going to make. And then you add in your fixed costs like your rent. So they told us that it cost this automobile company $8,000 to make each vehicle. So if they make 1 car, it's going to cost them $8,000. If they make 2 cars, it's going to cost them $16,000. If they make 3 cars, it's going to cost them $24,000. It's just the 8,000 times the number of cars. That's the variable cost of this model. That's what we're talking about here. The cost per car times the number of cars. That's the variable cost. Then you add in your rent, which is not based on the input, your rent being the $20,000 a week. So your cost function would be the $8,000 per car times the number of cars. We've said X is the number of cars. X is the number of cars sold. So this is the variable cost, plus then we have our fixed cost, which was the rent, the $20,000 a week. So this is all in weeks. So if this company makes 0 cars in a week, they're going to pay $20,000 in rent. If they make one car, they're going to pay the 20 grand in rent plus the 8,000 to make that one car, which is 28 grand. Now, if they sold that car for $20,000, if they only make one, they're going to lose money because all they're going to be able to do is cover their rent and not that first car they made. But if they made two cars, that's $16,000 to make the cars, 20,000 in rent, that'd be 36 grand total. If they sold it for 20,000, they'd have $4,000 in profit. Because 2 times 20 is 40 minus the 36. If they make a lot of cars, they make a lot more. Now, again, I was just spitballing some revenue numbers. We actually have a guided revenue function. So we have our cost function. We have our revenue function. That means we can find our profit function. As a reminder, profit is the difference of revenue and cost. Money in minus money out. So P of X, let's do this in, I don't know, purple, I guess. This is the revenue minus the cost. The revenue minus the cost. It's the red minus the green. All right, so now just doing everything in purple, that's the 22,000 x minus the 70 x squared. That was this. Then we go minus the cost function. Now the cost is multiple terms, so guess what? You need a parentheses. Then our 8,000 x plus 20 grand. Revenue minus cost. You have to know that in this course. So therefore our profit function, I think I changed purples. That's okay, I hope. We can distribute the negative, so we get 22,000 x minus 70 x squared minus 8,000 x minus 20,000. So our profit is, let's actually get these in descending order. So the minus 70x squared, that goes first. We're done with that one. Then we have the 22,000 minus the 8,000x, which is a plus 14,000x. Where'd the 14 come from? 22 minus 8. And then the minus 20 grand at the end. This is our profit function. This is what we want to optimize. How do we optimize something? We take its derivative, we set it equal to 0 to find the critical numbers, etc., etc. So P prime of x. Bring the 2 down and multiply it by the 70, the negative 70 to get a 140, negative 140x. The 14,000x, taking that derivative is just a plus 14,000. Taking the derivative of negative 20 grand is 0. We set this equal to 0 to find the critical numbers. So we go 0 equals negative 140x plus the 14,000. You could add 140x or subtract 14,000, doesn't matter. I'm going to add the 140x. I just like to go ahead and get that positive first when I can. So that equals the 14 grand. It's not wrong to have done it the other way. Divide both sides by 140. If you did it the other way, you'd be dividing by a negative 140. Ultimately getting that x, scroll please, is equal to, well, the zeros cancel and 14 divided by 14 is 1, so that's 100. So there's only one critical number. This is our critical number. Now, there's something interesting about this problem. I said that in general, when we're dealing with these optimization problems, you're given bounds. This A to B, 0 to 2 million or something like that. This one had bounds, 0 to 3. This one had bounds, -4 to 1. I didn't give bounds. What are the bounds? Well, 0 must be the left bound. Why? Because why would you make less than 0 cars? You literally can't make a negative number of cars. The smallest number of cars you can make is 0. Remember, x is the cars. You can't make negative cars, so 0 has to be the left bound. So we're going 0 up to something. So the question is, how do you find the upper bound? And what I'm going to suggest that you do is you go to a picture. You go to the graph. Now, you don't necessarily have to graph this. There is a way to do it without the graph. And it's based on the profit function. If you set this equal to 0 and solve it via the quadratic formula, then you can find your upper bound, but that's just not going to be the most easy thing to do for us. So let's pull out our calculator. Let's go to the graph. And we're going to get the graph of -70 x squared plus 14,000x minus 20 grand. Now, this is a quadratic function. The profit is quadratic and its leading term is negative. So this is what I expect the graph to end up looking like. Because the graph is again quadratic, because the function's quadratic and it's got a negative leading coefficient, this graph is going to look something like this. It has to look like this. Oops, I erased the wrong part. That was weird. It has to look like this, which means that somewhere there has to be an absolute max. We know we don't want to have a negative profit, so we should probably stop at where the profit is negative. That's going to be my suggestion on where to do the upper bound. So we got our graph. If we just go to graph, this is going to look terrible because we see numbers like 140 and 14,000 and whatnot, or 22,000, excuse me. And no, 70x squared, 14,000 and 20,000. Those are really big numbers, so we probably need to zoom out a lot on this thing. A lot, a lot, a lot. So let's just zoom out. That still looks pretty bad. Maybe not just zooming out. Maybe just go to the window. Let's make the x minimum 0. We know we can't go past 0. X maximum, let's start with 20. And let's just make the y numbers. The biggest number I saw up there, the linear value, that is to say, was the 20,000. Maybe let's just double that and start with 40,000. So let's go from -40,000. Well, we don't even want a 0 profit, so let's make that like a -1,000. And let's make the y maximum, I'm just guessing, 100,000. Maybe that's too big, maybe that's too small. I know I said 40 originally. All right, so now this looks like a line. We know it should look like a parabola, so we're still not zoomed out enough. We're not high enough, and we're not far enough right. So let's make the x maximum, I don't know, 50. And let's make that y maximum 1 million. Maybe that's too far, maybe it's not. All right, we're still growing at oh geez, what was that number? I put it at 50. So let's maybe take this to 200. There we go. There we go. Now I can see the peak of this graph, and I can see that eventually the profit goes to negative. And I can just trace over here. I type 400. I type 400, not 40. what was the Windows maximum at? 200, excuse me. I don't know why I thought I had 400. Let's try 190. We still have a positive profit. Let's try 200. We're at negative 200, sorry, negative 20,000. So if I actually go to calculate and find a 0, I can go to the left. I want to make sure the y value is positive, and there it's positive. And then I can go until I see the y value is negative. There it's negative. You can hit enter for the guess. And it says it's like 198 and some change. Well, I mean, that gives you a y value of 0. That's what that says. 1 times 10 to the negative 7 is roughly 0. So 198 and a half is about the maximum. So let's say it's 199. Okay. Now all we got to do is plug these in to the original function and see which one spits out the biggest number. So P, which the original function I did was in purple. So let's do the window of 0 to 199. We'll do P of 0, which that would be negative 70 times 0 squared plus 14,000 times 0 minus 20 grand. So when you plug in 0, you get negative 20,000. If you don't make any units, you're paying rent. That's what that says. So that's definitely not it. We don't want negative profit. How about P of 100 cars? If we make 100 cars, which we found to be a local extrema, that would be negative 70 times 100 squared plus 14 grand times 100 minus 20 grand. 100 squared is 10,000, just double the zeros, then multiply by negative 70, so that's negative 7, 0, and then 4 more, 1, 2, 3, 4. That's negative 700,000 plus tack on 2 more zeros to that. It's 1.4 million. 1, 2, 3, 4, 5, right? I did say that right. Yes, I did. Minus the 20 grand. $1.4 million minus $700,000 is going to be positive 700,000. Minus another 20,000 is 680,000. So at 100 cars made per week, the profit is $680,000. You can even see that in the calculator if you don't want to do the work. Just trace and type in 100. Enter. Boom, 680,000. Now, I think it's very obvious looking at the picture, that's the highest profit. No matter what you plug in as a right bound, it just keeps going lower and lower and lower and lower and lower. Whether you plug in the 200 or the 199 that I said, and the 199 is really supposed to be 198 and some change, but you get the idea. They're going to be really close. And when you do this, you're going to get let's just type it in. Skip the work this time. Negative 6,070. Something you definitely don't want. You don't want to pay net. You don't want a profit of negative $20,000. You don't want a profit of negative $6,000. You want a profit of $680,000. This is the highest. So therefore, that's the maximum profit. So the answer to A, how many cars should be produced each week to maximize profit? 100 cars. For what price should they be sold? We have not figured that out, but we have figured out what the maximum profit is. We figured out A and C, but not B. We didn't do them in order, but that's okay. So part A was 100 cars. Part C was a profit of $680,000. And these are both as a per week Part B, which they said was what price should what price should they be sold for? Well, we use our price function. Our price was the thing they gave us, this 22,000 minus 70x. So we do P of 100, because we're going to make 100 cars. So that's the 22,000. Erase that. Minus the 70 times 100, which is 22,000 minus 7,000, which is 15,000. So this company produce 100 cars each week, a price of $15,000 to get a profit of $680,000, again, each week. If they produce 99 cars, their profit will be smaller. If they produce 101 cars, their profit will be smaller. And again, you might just instinctively think, hey, why not make more cars? And if they sell, then you make more money and you make more profit. Well, the more cars you sell, the less the demand might be there. The more cars you sell, maybe your factory is getting too tight. There's too many people in the factory. You don't have enough space. There are diminishing returns in productive qualities that tend to have a maximum output that you should produce to maximize your profit. There are a lot of different theories on how you can maximize profit in economics. We are not getting into that nitty-gritty. But one of the classic examples to maximize profit is to have the marginal revenue match, in other words, equal marginal cost. In other words, when the revenue you're bringing in is changing at exactly the same rate as the cost it is to produce them, that's when you can, that's one of the classic ways to maximize profit. Your marginal revenue matches your marginal cost. Believe it or not, this is extremely easy to prove, and it's one of the few proofs that we'll actually do. We know, let's go back to red. We know that our profit function is revenue minus cost. Or let me just drop the variable dependencies. P profit, that's a capital P, not lowercase p for price, which that kind of looked like a uppercase P there. That's annoying, but this was price. Okay, so this is profit is revenue minus cost. How do we go about maximizing something? We take its derivative and we set it equal to 0. So take the derivative. The derivative of profit is profit prime. This is a subtraction, so you can take those derivatives differently. So that's revenue prime minus cost prime. Then we set it equal to 0. So we get 0 equals R prime minus C prime. We can then add C prime to both sides and solve for R prime. And what we get is that C prime should be equal to R prime. C prime is marginal cost. R prime is marginal revenue. Easy. How do you maximize profit? You want to produce when your marginal revenue matches your marginal cost. With these revenue functions, historically speaking, you don't want to produce 0 items. Why would you want to produce 0 items? You're not going to profit off of that. And you don't want to produce the number of items that brings your curve back down to 0. So what's interesting is with profit functions, the endpoints are almost unnecessary to test. I mean, I don't even want to say almost. They are unnecessary to test in our class. There are times when they're important to test if they don't give you bounds to begin with. Now, again, this is if we don't give bounds. If I gave you bounds straight up, then you have to test the bounds. But if there are no bounds given for a profit problem like this, typically you can skip checking the endpoints because the endpoints are going to make zero profit, and you obviously don't want zero profit. So that's a fun little example. All right. Next up, example 3. Another word problem. Our favorite, right? Farmer has 1,000 feet of fence and wants to build, oops, we got a question. Yes, you are correct. Example 4. I don't know why I said example 3. Even the piece of paper I have in front of me says example 4. All right, example 4, thank you. A farmer has 1,000 feet of fence and wants to build a rectangular enclosure along a straight wall. The side of the wall needs no fence. Find the dimensions that maximize the area of enclosure, as well as the maximum area. This is the classic horse pen or gardening problem, no matter how you want to look at it. And if you had pre-calculus, you should have seen one of these at least in there. But we handled it a little differently. Instead of handling it as a calculus problem with derivatives, we knew in pre-calc it was a quadratic function, so we knew that the vertex was always going to be the location of the max and the min, and the vertex has that formula negative b over 2a that you should still honestly remember. You can actually use calculus to prove that the maximum of a quadratic occurs at negative b over 2a. It might even be a homework problem. That's me whispering in case you didn't realize that. Okay. Picture's worth 1,000 words. So why do we have a side that doesn't need fencing? Maybe we're putting this along a barn or a house, or maybe there's just a wall that's already there. So the picture is going to look something like this. So here are the sides that need fence. So there's fence here, there's fence here, and there's fence here. Then we'll have our wall, and I'm going to draw it kind of wavy. It could be a river as well, assuming that it's perfectly straight. We're just going to say that this is our wall. It's already there. There's no way for us to make this garden or horse pen any longer than the wall. It's an infinite long wall in theory. So we have 1,000 feet of fencing, and we're not going to put fence along the wall because that's just a waste of materials. Because every inch or every foot of fence we use here is a foot we can't use over here, and that's going to make the area shrink. And we want this area to be as big as possible so our horse has got plenty of room to roam, or we've got a ton of room for our garden. So this is a rectangle. Rectangles are easy. Rectangles have length and width. Let's call the side that only has one length of fence x, and let's call the vertical ones y. Now, if that's y, this has to be y. They have to match. So x is the length parallel to the wall, y is the length perpendicular to the wall. Do you have to do them this way? No. You can reverse the x's and the y's. You can have two x's and then a single y. Now, because this is a rectangle, it has a very obvious formula for area and perimeter. Area is length times the width. Perimeter is just the sum of the sides. So the area of this would be the length times the width, which is just x times y or y times x. The order doesn't matter. The perimeter, which I'm going to put in quotes because it's really just the perimeter of fence. We're not going to add up 4 sides. There's only 3. Now this problem can change. You can actually put in dividers as well, and then it's not a true perimeter. It's just the perimeter of fence. It's the sum of all the different fences. So we're adding up 3 sides. There's a y plus an x plus a y. Y plus y is 2y. So that's x plus 2y. Again, y plus y is 2y. So there's 2 different equations for this problem. When you deal with an optimization problem that has 2 equations with 2 variables, because this is kind of like a system of equations, we haven't done a lot of problems in here where there are x's and y's. It's usually just x's, or any particular letter. In the next section we go to in 3.6, we're going to start dealing with multiple variables more consistently. We'll have x's and y's littered all over the place and learn how to do their derivatives and such. But for now, we're just introducing the fact that we can have multiple variables, but we're not quite ready to do that extended concept yet. So what we need to do is focus on what we're actually trying to optimize. We want to maximize the area. This is the area formula, so we need to maximize this. This is the thing that we'll be taking a derivative of, ultimately. I want to type some notes down here below. We want to maximize the area function. However, we currently don't know how to take derivatives of multiple variables. So we need to eliminate one of them. Doesn't matter which. I much prefer to eliminate the y and only have this as a function of x because that's what we traditionally see. However, it doesn't matter, and that's why I've set it up this way, where we're actually going to solve for the y because it's easier. To do so, use the other equation, in this case, the length of fence, and solve it for 1, and plug into the area equation. Dot, dot, dot. We also know the number, the perimeter. It's 1,000. So instead of writing perimeter equals x plus 2y, I can write 1,000 is equal to x plus 2y. This is our fencing equation, the length of fence, the quote perimeter, because we know we have 1,000 feet of fence. Let's solve this for x because it's easier. You can certainly solve for y, it's just 2 steps instead of 1. All I got to do is subtract 2y on both sides, and you'll get 1,000 minus 2y is equal to x. This is important. This is a pivot point for us. This is a substitution method for systems of equations. If you're a little rusty with that, it's prereq material, Google, previous homework problems for review, etc., etc. So we're going to take this and we're going to plug it into the area equation. And there's another name for this. It's called the primary EQN equation. The primary equation is the one you want to maximize. The secondary equation is the one you have to use to plug into the primary. And this is a pretty common setup. So the area equation was A equals x times y. So A equals x times y, let me switch colors, is going to turn into A equals x, that got ugly, times 1,000 minus 2y. Wait, what am I doing wrong? I'm doing something wrong, aren't I? I have a bad habit. this says x equals, and I tried to plug it in for y. That was a goof on my part. X times y, this is x. So this right here is what goes there. So that's 1,000 minus 2y times y. Again, this was x times y, but the x is really 1,000 minus 2x. Excuse me, minus 2y. Blah. Like I said, I'm doing this in an uncomfortable way so that you're used to doing it either way, but you can tell how uncomfortable it is for me. I usually just instinctively always solve the secondary for y, so then everything's an x. But there's nothing wrong with doing it this way. I'm trying to keep us all on our toes. So this is the area equation. We now only have one variable. We can now do our calculus. We take its derivative. So we do a prime is equal to, well, that's a product. Let me pause on that. Let's distribute the y first. So area is 1,000y minus 2y squared. Now let's take its derivative. That way we don't have to use the product rule. We could have done it that way, but product rule is annoying when you don't have to. So that's going to be 1,000, because the derivative of 1,000y is 1,000, then minus, drop the 2 out front and multiply it, so you get a 4, decrease the exponent by 1. That's 1,000 minus 4y. That's our derivative of our area. That describes how the area is changing in relation to y, in relation to the length of the side of fence where there's 2 of them. Don't worry about overthinking that. Just go through our classic optimization. Set it equal to 0. So we go 0 equals 1,000 minus 4y. Solve this in any way you like. I'm going to add 4y to both sides. You could subtract 1,000 instead. So we get 4y equals 1,000, or you would get negative 1,000 equals negative 4y. You then divide both sides by 4. 1,000 divided by 4 is 250. So we get y is equal to 250. Y was the length of fence perpendicular to the wall. That was the fencing where we have 2 of them. Since this is the length of fence and we said we were in feet, this is 250 feet. And note there are 2 of these. So that's 500 feet of fence that we've used. We have got 250 feet on the left, 250 feet on the right. It should actually be ridiculously easy to figure out what this should be because we had 1,000 feet in total and we're using 500 of it currently. We just subtract 1,000 and 500. If you don't want to do that, any of that implicitly, just go back to this. The length of fence, which was right here. X is equal to 1,000 minus 2y. We're going up here now. Going back to the equation that we substituted in. It's a pivot point because we're going to use it and we're going to come back to it. We know the value of y now. So we say 1,000 minus 2 times 250 is equal to x. 2 times 250 is 500. 1,000 minus 500 is 500. X was another type of length of fence, so it's 500 feet. And there's only one of these. So we got one side that's 250, this side that's parallel to the wall is 500, and then this side is 250 as well. Those are the dimensions that should maximize the area. Now, if you don't believe me, the area formula is quadratic. It's got a negative leading coefficient, so it's going to point down, and instinctively it has to be the maximum. You can actually prove this. Just by taking the second derivative. Negative, concave, down, and thus a max. If it was positive, it's concave up and thus a min. Well, a double prime, a prime was the 1000 minus 4y. The derivative of 1000 is 0. The derivative of negative 4y is negative 4. So it has to be a max because this is negative. It's negative everywhere. It's always negative. Whenever your primary function's quadratic, by the time you get to the second derivative, it's just going to be a constant. This can also be seen in the last example. If you didn't want to have to check the bounds since it was an unbounded problem, where is it? Here's our profit function. If you took its derivative, the derivative would be negative 140, which means it's concave down, which means it looks like this and has to be a max. There are lots of ways to prove that it's a max and not a min. And you are technically supposed to do that, but in the homework, you kind of get a pass on it a lot of the times. So what are the dimensions? DIM means dimensions. We want to build a 250 by 500 foot garden with two sides of 250s. It does matter. If you swap it, if you do this is 500 and this is 500, you can't even have this side because you've already used your 1,000 feet of fence. I think that makes sense. I hope that makes sense. It has to be 250, 250, and 500. If this had been 500, that makes this 500, and then you're just sandwiching the fences together on top of each other, and there's no area. But we also asked what was the maximum area because we want to know how much space our horses have or how much space our garden has. Especially with the garden, we got to go buy nutrients and stuff. We got to know how much to buy. Well, we had our area function, which is the x times the y. You could actually use the other version of it. You can use 1000y minus 2y squared or 1000 minus 2y times y. But this is the easiest version of it if you have x and y, so why not use it? So this is just 200. Let me write them in the right order. 500 times 250. God, that looks awful. Five times 25 is 125. Tack on the zeros, 1, 2, 3. And if you answered this 125,000 feet on a handwritten test, I would mark that wrong. Because it's not feet, it's feet squared, because that's 500 feet times 250 feet. Feet times feet is feet squared. All right. So let's do this again, but change it a little. Example 70. No, I'm kidding. Example 5. Same idea as before. 1,000 feet of fence. With a no fence wall. A non-fence needed wall with a no fence needed wall. But now we want a divider perpendicular to the wall. Find the dimensions, maximize the area as well as the area. So we still have 1,000 feet of fence, but now we want to have a section for our horses and a section for our garden. I know that sounds a little silly. Maybe we got a section for horses and a section for pigs. I don't know. Two animals that don't necessarily need to intermingle. So we want to keep them separate. So now, what our drawing looks like, we got our fence here, we got our fence here, we got our fence here. I'm just going to do F for fence, F for fence, F for fence. We got our wall along the top. Then we don't need fence. But now we want a vertical divider. And I didn't actually say where to place it. And in fact, the placement of it doesn't matter because it's not going to change the area. But I did mention that it needs to be perpendicular to the wall. So this is not what I'm doing. That would be parallel to the wall. We're doing this. Now it could be there, or it could be here, or it could be here. The actual location will not affect any of the math here. I can guarantee that. Let's split it in equal parts, but maybe you're dealing with horses and pigs and the horses need more room, so maybe you put it over here instead. I could put multiple enclosures. I could put one here and one here and one here, but we're just dealing with the one. So our area, the formula for this doesn't change, and let's stick with the same x's and y's. So we called the vertical one's y and the horizontal one x. So this is our x. And that's the whole distance across, not just the little slice. Then this is a y and this is a y. But we have this third length that is the same, so that's also a y. The area is still x times y. That's not changing. This length times this width, x times y. We're talking about the total area, so we don't have to do two separate areas. But now the fencing perimeter, we're not just adding the outer one, we also have to include the fence that's in here. So there's 3 of these y's and an x. So it's 3y plus x. The rest of the math is hardly going to be any different. We're going to need to take the perimeter one, which is 1,000 feet of fencing, 3y plus x. We're going to solve that for x. We're going to plug that into the area so that we only have one variable. We're going to take its derivative. We're going to set it equal to 0, and the rest is history. So for that 1,000 minus, I'm sorry, I don't want to jump the gun. The 1,000 equals 3y plus x. We'll subtract 3y on both sides to get 1,000 minus 3y is equal to x. This is our important equation that we'll use now and come back to. So we'll plug that into area. So our area, A, x times y is now 1,000 minus 3y times y. We substituted the x as 1,000 minus 3y. Let's distribute this. So we get A equals 1,000 y minus 3y squared. You can reorder if you want. Now we take the derivative. Let's use a notation I haven't in a while. Let's, instead of writing a prime, let's use dA over dy, because the derivative is taken with respect to y, not x. If these were x's, this would be an x, but they're y's, so this is a y. The derivative of 1,000y is 1,000, minus the derivative of 3y squared is 6y. Set it equal to 0. So we go 0 equals 1,000 minus 6y. Add 6y to both sides. You get 6y equals 1,000. Divide both sides by 6. And you get y is equal to 166.6 bar. And that's in feet. Now we plug this in to that substitution equation, to the secondary. We don't plug it into the x, we plug it into the y because this is a y value. So we're plugging into that little asterisk equation. So we say 1,000 minus 166.6 bar times 3. I'm supposed to write the 3 first, excuse me. That should be equal to the x. 3 times 166.6 bar is 500. That's 1,000 minus 500, which is, interestingly enough, still 500 feet. So our dimensions, it's going to be 166.6 bar feet by 500 feet. And there's 3 of these and one of these. So our area, the maximum area, will be the 166.6 bar times 500, which if you do that math, you're going to get 83,000, and then it's just a bunch of threes. Feet squared. I want us to pay attention to these numbers. Let's look at the last problem. We made a 250 by a 500. And then the area that we got was 125 grand. This time, we make a 166.6 by 500. So that 250 has gone down significantly because we needed the extra bit of fencing. Basically, we took some of the fencing from the left wall and right wall and made the divider. So we pulled in the length of X's fence, we pulled it closer to the wall so that we could have the divider, and it brought the maximum area down from 125,000 to 83,000. That's a significant effect. We just lost like 42,000 square feet. But because we needed a divider, that's what we had to deal with. Now you might say, well, just go buy more fencing. Maybe you're out of money at this point. I don't know. So here's what's cool about this problem. If I threw in another divider, that just means there's a 4 here, which just changes this number, which just changes this number, and I bet you $1,000,000 that 500 is the same. Now, if I throw a parallel divider to the wall, that will change the ratio and proportion of numbers a little bit. But it's just fun how you can have kind of the same problem, but throw in more and more different little dividers and get different numbers. But again, it's really interesting that the length of the wall the length of fence parallel to the wall is not affected by dividers this way. I bet if you did a divider the other way, it probably wouldn't affect the other length, the Y length. So that's a fun variation to that problem. And there's only one last thing I want to write. Let's just insert a new page to do that. There we go. Oh, perfect, that worked. So the primary and secondary thing I mentioned, let me just type it out. Secondary equations, let me say it a different way. The secondary equation is the one that gets substituted. Primary equation is the one that gets optimized. Now, both of the problems we did were maximizing, but you could minimize something as well if that's what was important. Minimize deaths of a virus, minimize losses of stock revenue, or stock profit, excuse me, not revenue. Both relative to things going on right now. All right. Hold on, I need a minute. Something's happening at my house. Give me about
Sorry, I was supposed to stop that a minute ago, and my dog was distracting me. So Sorry about that again. So that is going to be it for the evening. Like I said, we were just going to cut it at 3.4. You'll get an extra 20 minutes of your time. Well, I guess 19 now after that. So 3.2 and 3.4 were finished. So they're due in 2 weeks. You get a full 2 weeks for those. So no excuses to not get those done by the end of the 14th, 11:59 p.m. per usual. Hopefully we've got 2.2, 2.3, and 3.1 completed at this point, but if not, you got a few hours left to knock those out. And, go ahead and start studying for the exam, for the test, for the chapter 2 and 3 test while you're on spring break if you have any chance. But besides that, do enjoy your break. Maybe you get to take a short little trip or something, or just have a nice relaxing time at home and get a little math done on the side when you have a chance. But as always, if you have any questions, shoot me an email. If you think we still need to talk about your test score, shoot me an email, whatever it is, we can talk. Besides that, have a good 2 weeks, have a good break, and we will see you on the 14th. Take care, everybody. Good night.